What if I told you that there's a chip out there that doesn't even use electricity to compute? No transistors flipping on and off, no heat sinks the size of a car radiator, just light. Pure, raw, physics-defying light doing math faster than anything silicon has ever managed. And this is not a concept paper. This is not some PhD student's whiteboard fantasy. This is happening right now in 2026 inside one of Europe's most powerful supercomputers. I genuinely think this is one of the biggest hardware shifts of our lifetime, and let me show you why. Alright, let's start with the actual problem here, because there is a very real, very expensive problem that the data center industry really doesn't want to talk about out loud. GPUs are incredible machines. The H100, the B200, NVIDIA's whole Blackwell lineup, these are genuine engineering marvels. But here's the thing nobody leads with. Every single new generation of GPUs eats more power, runs hotter, and needs more cooling than the one before it. Right now, cooling alone accounts for up to 40% of total data center energy. Not compute, not networking, just keeping the hardware from frying itself. That's a wild number when you sit with it. And it gets worse. A single AI service like ChatGPT burns through over 564 megawatt hours of electricity every single day. To put that in perspective, that's roughly 100 times the annual electricity consumption of a German household. Yes, you heard that right. Per day. I'll let that sink in. The deeper issue is actually architectural. Modern GPUs are built on what's called the von Neumann model. You compute in one place, you store memory somewhere else, and data is constantly shuttling back and forth between the two. At the scale of modern AI, that data movement costs an enormous amount of energy. Researchers call this the memory wall, and hitting it with big language model feels about as pleasant as it sounds. Then there's the Moore's law. The old idea that transistor density doubles every 2 years is basically dead past a certain point. We're packing so many transistors onto chips now that electronics are literally jumping across gaps they're not supposed to cross. Quantum tunneling. At that scale, physics start working against you rather than for you. Silicon is running out of room to grow, so the industry genuinely needs something different. Not a faster GPU, a completely different way of thinking about computation. Now, this is the part I feel genuinely excited for, and I think once you understand the basic idea, you'll get why. Photonic chips don't compute with electrons at all. They use photons, which are particles of light, and that one substitution changes almost everything about how the chip behaves. Light moves much faster than electrons in a wire. It produces basically no heat on the chip itself, and here's what really got me when I first read about this. A single beam of light can carry multiple different independent streams of data at the same time by using different wavelengths. So this is effectively different colors of light. This technique is called wavelength-division multiplexing, or WDM. So instead of processing one matrix multiplication and then the next, you can run dozens of them simultaneously in parallel through the exact same physical waveguide. Electrons physically cannot do that, but light can. The actual computation happens through a phenomenon called the optical interference. When two light waves meet, they either reinforce or cancel each other depending on their phase. That interference pattern is the math. A whole layer of a neural network can be processed in essentially one pass through the chip. No clock cycles ticking away, no fetch and execute pipeline. The calculation happens as a consequence of light traveling through the material. It's kind of beautiful when you think about it. The key material making this possible right now is thin film lithium niobate on insulator, which they shorten to TFL-NOI, so it can switch and modulate at tens of gigahertz and responds to electric fields rather than heat to change its properties. That means components don't thermally interfere with each other, which lets you pack them much more densely than anything you can do with silicon. On the software side, I know that the first question people ask is, do I have to relearn everything? And the honest answer is no. The companies building these processors have built compatibility layers on top, so developers can still write in Python, PyTorch, TensorFlow, whatever they're already using. The translation to optical operations happens underneath. That makes adoption a lot more realistic. Now let me tell you about the company I think is at the sharp end of all of this right now, and the deployment that made me take this whole thing seriously. Q.ANT is a photonics company based in Stuttgart, Germany. And what they've pulled off in the past year is something that genuinely would have read as science fiction not long ago. Back in July 2025, they delivered their first generation native processing server to the Leibniz Supercomputing Centre, also known as the LRZ, in Garching, Germany. This was the world's first deployment of an analog photonic coprocessor in actual operational live HPC environment. Not a demo unit in a lab somewhere, a working supercomputing facility that serves universities and research institutions across Bavaria and Germany. Then, in March 2026, literally just last month, Q.ANT deployed their second generation NPU at the same facility, and the benchmark numbers that came out of LRZ are hard to ignore. The Gen 2 architecture delivered more than 50 times higher throughput on matrix multiplications compared to the first gen chips, and 25 times faster interference on a ResNet 18 image recognition network. That's not iteration, that's a completely different gear. The headline specs for the Gen 2 NPUs are up to 90 times lower power consumption per workload and up to 100 times greater effective data center capacity. The chip produces zero on-chip heat, which means that you can largely forget about the massive cooling infrastructure that eats up so much of a traditional data center's energy budget. It slots in via standard PCIe interface, so it drops right into existing server racks without needing to redesign the whole facility. LRZ is currently running it on real workloads including AI interference, computing vision, and scientific simulations covering climate modeling and material research for fusion energy. Q.ANT CEO Dr. Michael Furtz said something that I keep coming back to. What took 10 years for digital computing, we've achieved in 1 year with photonics. And the benchmark jump from Gen 1 to Gen 2 in 12 months honestly supports that claim. The project has backing from German Federal Ministry of Research of Technology and Space, which tells you that Germany is treating photonic computing as a matter of national strategic importance, and not just an interesting experiment. Q.ANT isn't the only player either. Chinese research teams from Tsinghua and Shanghai Jiaotong University built a chip called LightGen, a fully optical processor with over 2 million photonic neurons. In published researchers, they demonstrated more than 100 times better performance than NVIDIA GPUs on specific tasks like image synthesis and style transfer. Another chip called XL delivers 4.6 petaflops on a power draw that would make any data center manager weep with joy. This is the global race now, and it's moving fast. Okay, I want to be upfront here because I genuinely believe in this technology, but believing in something doesn't mean pretending the problems don't exist. The biggest issue is the one I touched on earlier. Photonic chips cannot store data. There is no such thing as a practical optical RAM right now. So every time the chip needs data that isn't actively flowing through it, it has to reach out to a conventional electronic memory, and every time you convert between the optical domain and the electrical domain, you pay a penalty in time and energy. Engineers call this the conversion penalty, and depending on the workload, it can claw back a real portion of the efficiency gains you were counting on. The best analogy I can think of is, imagine building the fastest race car in the world, then realizing your pit crew has to bring the tires on bicycles. The car is legitimately extraordinary, but you are going to spend a lot of time waiting at the pit stop. Researchers are currently developing something called a photonic latch, basically an optical version of SRAM cache that would keep data in the light domain without converting it. It's a promising direction, but it's not shipping in anything yet. There's also the flexibility problem. Photonic chips are phenomenal at specific types of math, matrix multiplications, Fourier transforms, convolution operations, and for those, nothing touches them but general purpose arbitrary logic, that still needs a CPU or GPU sitting alongside the photonic chip. Every real-world deployment right now is a hybrid step for exactly this reason. The photonic chip handles the heavily mathematical lifting, and conventional silicon handles the rest, and fabrication is genuinely hard. Thin-film lithium niobate is not a material that TSMC or Samsung have been perfecting for 40 years. Production yields, long-term reliability, and behavior at scale are still needed to be demonstrated consistently. That's the part where the LRZ deployment is actually designed to test. So, what's the realistic picture here? Photonic computing is not replacing GPUs next year. Your gaming PC is, well, fine. But that's not actually the point. What photonic chips are doing right now is establishing themselves as the only credible answer to an energy problem that is genuinely threatening to slow down the entire AI industry. The math just doesn't work for silicon for much longer. AI workloads are compounding faster than power grid can keep up with it. You cannot build a gigawatt data center for every major model upgrade. Something has to give, and 90 times lower power consumption per workload is not a minor efficiency gain you can dismiss. That changes the economics of the whole enterprise. My honest read on the timeline is that from now through 2030, photonic coprocessors become standard components in specialized HPC facilities. Scientific research, real-time medical imaging, climate modeling, large-scale AI inference. After 2030, if the memory problem gets cracked and fabrication scales up properly, the footprint of this technology gets much, much larger. What Q.ANT has built at LRZ is important because it's the first concrete proof that photonic computing holds up outside a controlled lab setting. Under real operational conditions, with government backing and institutional accessibility, that is the line promising research and real technology, and they've crossed it. Computing with light. It still sounds like something out of a novel, but here we are in 2026 watching it run inference jobs at supercomputing centers, and honestly I think we're going to look back at this period as the moment it all started to shift.